In this video, the MYRTUS Reference Infrastructure is showcased through two demos. The first highlights the integration work completed in the first half of the project, delivering a cloud edge continuum spanning all involved partner sites. The second demonstrates the potential of this infrastructure to deploy complex applications, paving the way for the project's use case-specific algorithms. For these demos, we've built a cloud edge continuum composed of geographically distributed clusters from project partners, one in Spain from UPM, two in Italy from Unica and Abinsula, and two in the Netherlands from TNO and Hyro. All clusters are interconnected via Liqo, forming a unified cloud edge continuum. This architecture is shown on this slide. In the center, the UPM cluster acts as the master. The other clusters are exposed to UPM as Liqo virtual nodes. So from UPM's perspective, the entire multi-cluster infrastructure is available. Concretely, the TNO cluster offers cloud-grade compute nodes, while Hyro and Abinsula provide fog-like nodes. In turn, Unica and UPM contribute FPGA-based edge nodes. This way, users can leverage the nodes that best fit their performance, power, and latency needs. With that brief introduction to the MYRTUS infrastructure, let's start the first demo, where we show the integration work of this first half of the project that resulted in a cloud edge continuum infrastructure. The infrastructure of this demo can be inspected with this command, which lists each remote cluster by name as well as its health status, meaning it's ready to receive computation. Each cluster in this infrastructure is composed of a set of computing nodes. This command shows the current set of available nodes. You can see we have a dedicated node per remote cluster, Hyro, TNO, Unica, etc., as well as nodes that are local to the UPM cluster, the ones whose names start with MYRTUS. The reason for this difference is that remote clusters are represented by Liqo as single virtual nodes that aggregate their resources. Those remote clusters may contain multiple nodes behind the scenes, while for the local cluster, all of its nodes are listed individually. Let's dive into the demo. We'll run a Hello World application on each of the clusters in the described infrastructure, both local and remote. The starting point is to create a Kubernetes namespace for this demo. Then we offload that namespace to the remote clusters using this command. We preserve the namespace name and allow pods in that namespace to be scheduled on both the local cluster and the remote ones. Next, let's review the application to be executed, which is embedded in a Kubernetes manifest, a description of a Kubernetes object. The manifest for this demo will create a series of pods, each running the same Nginx container, but scheduled on different remote clusters, specified by the cluster names. To deploy these pods, we apply the manifest to the demo namespace. If we check the running pods, you'll see them starting up, thanks to Liqo working under the hood in each of the remote clusters. After a few moments, all of them are running smoothly. We can verify that they're actually running on the remote clusters by querying each remote cluster directly with the Kubernetes command line tool to list the pods currently running there. You can see that for each remote cluster, there's an Nginx pod running on its local node. Beyond offloading an application to a local or remote cluster, it's often useful to target a specific node within a remote cluster. To do that, we'll use a Liqo mechanism called nodebind, which enables selecting a particular node in a remote cluster. For this part of the demo, we'll again deploy a series of Nginx pods. this time applying the manifest from a different cluster and targeting specific nodes within UPAM's cluster, effectively turning it into a remote cluster. In particular, we'll use the set of nodes shown by this command whose names start with MYRTUS. We first create a new namespace and offload it. In this case, the offloading strategy is set to remote, so the pods are scheduled only on nodes that belong to remote clusters, which is the goal of this demonstration. The Kubernetes manifest for this application is similar to the previous one. It deploys a pod with an Nginx container. However, since we're selecting a specific node within a remote cluster, instead of letting Kubernetes handle lower-level scheduling, we include an annotation that precisely indicates the target node, and that is handled transparently by Liqo. We do this once per pod/node pair. Next, we apply the manifest to the existing namespace. After that, you can see a series of pods created, each on the specific node we selected. This concludes the demonstration. We showcased how to offload a pod to different clusters in a Liqo-enabled computing infrastructure, and how to target specific nodes within those remote clusters. Next, the second demo illustrates how this cloud edge continuum can be leveraged to run a realistic application, moving tasks across the continuum based on user needs. To that end, we developed a visual proof-of-concept application to showcase the capabilities of the MYRTUS Reference Infrastructure. The application is a UAV visual navigation pipeline for GPS-denied environments. The motivation is that UAVs often need precise position updates in places with limited satellite signals, for example, in valleys or areas with deliberate interference. In such scenarios, the ground serves as a reliable reference. Pattern recognition identifies features like roads and field boundaries as a stable visual aid independent of external infrastructure. At its core, the application matches a camera frame from a downward-facing UAV camera against a pre-computed terrain map. It consists of 3 kernels: key point extraction, which identify interest points used as visual anchors; key point description, which compute descriptors around each key point to enable comparison; key point matching, which compare frame descriptors to the map's descriptors to find the best alignment. The result is the estimated location of the frame on the map, allowing the UAV to localize itself. Let's jump into the second demonstration to analyze the potential of the proposed cloud edge continuum infrastructure when deploying these complex applications. The setup infrastructure for this demo, shown with this command, contains a set of computing nodes. Some of them, the ones starting with MYRTUS, are FPGA boards located at UPM and exposed as local nodes. The others are geographically remote clusters made accessible through Liqo. To run this demo, a dedicated Kubernetes namespace has been created, which already has some containers running. We are not going into their details, but they are basically used to expose the drivers required to access the FPGA hardware. Let's dive into the demo. The first step is to run a server application in the dedicated namespace. You can see now that it is creating the container. This server basically allows us to have a graphical user interface, you'll see it in a moment, with which you can decide to which of the available computing nodes, both the FPGAs and the remote clusters, you want to send the video processing request. Once the server is running, we can open the GUI. At the top, you can see several pieces of information, such as whether the server is available and we are connected to it, the number of frames per second achieved with the current processing, and the video being processed. Right below, you can select the amount of frames to process, as well as the specific node/board to which the computation will be deployed. Then, below that, you can see, on the left, the current topology of the cluster. Note that since no application is running on the nodes yet, the topology appears empty. You'll see in a second that when the apps run, the server populates this view with the nodes involved. Meanwhile, on the right, you have the pre-computed map to which the processing node will match the acquired image. Lastly, at the bottom left, you will see, in a moment, the current frame being processed by the system. So let's now run the applications on the FPGAs. To do so, I'll place here a terminal so we can see how the topology gets populated. To run the application on the FPGAs, we have a manifest that we need to apply, which deploys a set of containers, one to each available FPGA board. You can see here the containers being created in each node, and in the topology view, you can see them appearing as they start. Besides the hardware version, we can also run the app in software on the remote clusters using Liqo. This is done by applying another manifest, which deploys another set of containers. Again, you can see the containers being created and the nodes appearing under the Liqo segment. Now in the topology, you can see there are some remote nodes, accessible via Liqo, where the application runs in software. There are also FPGA boards placed locally at UPM. Among those, you can see three types: Pynq, UltraScale Plus, and Alveo, each with an increasing amount of reconfigurable resources, which comes together with higher power consumption, shown below the name of each board. Because of that, we developed a specific implementation for each of them, applying a higher degree of internal parallelism depending on the available resources, by leveraging certain optimizations, such as loop unrolling, pipelining, etc. Moreover, as you can see, there is a baseline flavor and an optimized flavor, which applies even more parallelism by having multiple replicas of each kernel, achieving higher performance. In summary, we can choose to execute the application on the node that best fits our needs, depending on the performance and power requirements of the scenario. We'll start with one of the smallest FPGAs, the Pynq, but using the optimized version. Since it is slower, we're going to process just 4 frames. What you'll see now, after a moment, is, at the bottom left, the frame being processed, and on the right, a blue square showing where the FPGA node has detected the frame matches the map. This is done for each of the frames, and at the top you can see the FPS obtained. In this case, it's around 0.3. If more performance is required, we can choose another board, at the expense of power. With the UltraScale Plus, for instance, the FPS we get is around 2.3. And for even higher performance, we can go to the Alveo, which in the baseline version reaches almost 4 FPS. And if we move to the optimized flavor, you can see we get almost 9 FPS. That was on the local FPGA boards. But we can also run the software version on the remote clusters using Liqo. Let's select the Abbey node. And you can see a red LED appears indicating it is busy, and after a bit, because it's software, you'll see the first frame. In this case, we get around 0.5 FPS. And so, you can see how we can move the application to different nodes to meet our requirements. I want to show you now the back and forth communication between the board and the server, so I'll attach to their communication like this. Now, to see something more interesting, I'll switch to a video that contains more frames and moves more smoothly, and I'll run the app on the fastest board but processing more frames. You can see that now, at the bottom left, the frames show the drone moving through the city smoothly. And you can see the blue square moving accordingly while the FPGA detects where each frame matches the map. And in the opened terminal, you can see the detections made by the FPGA for each frame. For instance, on the last one, you can see the frame number, the board processing it, and the coordinates where the frame matches the map. Lastly, I want to show you the power consumption metrics that we can obtain at runtime thanks to a monitoring infrastructure placed in the hardware. Note that in the GUI, we showed average values, but here you can see a high-resolution plot of those traces. What you see is, at the top, the power consumption waveform of the processor, in the middle, the power consumption waveform of the FPGA, and at the bottom, the start and stop signals of the hardware accelerators running in the FPGA. Together, these two demonstrations present the work developed for the MYRTUS Reference Infrastructure, which serves as a foundation for the next phase of the project.